Thank you everybody for joining in. Today we are starting with another review club and this is on Miniscript support in output descriptors. So this is about a PR that got merged quite a long back around 2020, 2022, 1 year ago into Bitcoin Core, like where it added the Miniscript support into Bitcoin Core. We'll talk more about what Miniscript support is and what it does. So let's dive into it, and we'll go by the summary document of Bitcoin Core Peer Review Club, which happened last year, May 18. This is also a very outdated part of the doc where it talks about first part, second part. We'll also like talk in first and second parts. We'll do two parts of this same concept in the next week also, but we'll keep the discussion for the first part on the conceptual level. We'll try to understand what miniscript is, what a descriptor is, how they combine together, and why they are useful, and why people are so hyped up about miniscript and descriptor these days. So we'll kind of like break the rule for this club. Yes, Ayush, it will be around 1 hour. We'll try to complete it by 9 to 9:10. And yes, so we'll kind of like break the rule today of like following the usual questions. We'll not go by them. Instead, let's start the discussion about like what can anybody describe in just basic sense like LE5 and what is a descriptor and what is a descriptor used for. So we'll referring to the output descriptor portion. Anybody want to give a shot what a descriptor is?
No, I'm not sure what it is. I'm learning it for the first time.
Okay, yeah, that's cool. Um,
So
okay.
descriptor means like it's the derivation how we get the private key output. I'm not sure if it's private or public key, but
Mm-hmm.
based on some key, how we
Mm-hmm.
derive. Yeah,
Yeah.
instead of just remembering a number, I guess this makes
Right.
it.
Right. So uh, here the sentence describe descriptors, output descriptors, a string that contain all the information necessary to allow a wallet or other program to track payments made to or spent from a particular script or set of related scripts. So as a wallet, like what is a wallet as a software? The essence of an wallet is like it's a software that tracks a certain bunch of script pub keys, like what we call as addresses. It tracks a bunch of Bitcoin address. That's how the wallet knows like what is your balance, how you can create a transaction, which UTXOs you have, and all this information. Right. So that is the essence of any wallet operation. What output descriptor is these are strings. These are specially made strings. We'll look into how these strings looks like, that contains all the necessary information that a wallet need to create all the addresses and the script pub keys and related scripts. Everything regarding scripts that a wallet needs to track can be derived from an output descriptor. So let's look at an example of some output descriptors, and we'll take a look at this document. So this is inside Bitcoin source repository, and if you go into docs, uh, release notes, not in release note, but yeah, in docs, you will see main folder, there is descriptors.md, and that descriptor file describes what it is for. So in script pub keys in Bitcoin, we know like there are different kind of script pub keys like P2PKH, P2PK, P2WPKH, and this type of pub keys follows a different set of rules, right? How do you solve them? How do you satisfy them? A descriptor looks like a string like this, which is say like PK and the public key. And it kind of make intuitive sense what this descriptor is trying to describe. So it's a descriptor, so it's a description of something, and that something is a script pub key inside the Bitcoin transaction output. And a PK descriptor basically says like use this public key, this is a public key starting with 0 to you, use this public key and create a P2PK script pub key. And you can identify any kind of P2PK script pub key that is created with this particular public key using this descriptor. So if you tell the wallet that my interested descriptor, the descriptor my wallet should be interested in looks like something like this, then the wallet knows like, okay, that's a P2PK descriptor with this public key. I know how a P2PK descriptor looks like. I know its structure. I know this public key directly has to go there, and rest of the stuffs. It knows the entire script pub key that it needs to track with. This is the most simplest fundamental one, but we can do more fun and cool thing with it. Second one is like PKH. It's the same thing. Here's a pub key, and you're saying like put it into a PKH type of output. Put it into a PKH type of script pub key. That I'll use output and script pub key interchangeably. They mean the same thing. Output is transaction output, which has one value and one script pub key. The script pub key is the locking script, and we are basically talking about describing the locking script. Here, by reading PKH, the wallet will go, oh, this is not just a PK. We have to take the pub key, we have to hash it and put it inside a P2PKH format. Then it knows the address that it needs to track to. Same thing for WPKH, same thing for SHWPKH. This is what is represented by a P2SH wrapped or wrap of a P2WPKH. Don't worry if you don't understand fully like what these things is. You can like search it up. These are like address type, different kind of, and they are used for different cases. The entire point is like using this kind of strings, we can very easily identify all the information that is required to create a P2SH, P2WPKH. Right, and then it can go into more complex stuff. Here's a sh multi. It means like this string together describes a 2 of 2 multisig. It's a multi of 2 with 2 pub keys. So it's a 2 of 2 multisig wrapped inside a P2SH. So the wallet knows how to derive the whole thing. So these are the ways of like very easily describe a script pub key system, and this is what a descriptor is. You can even do this. So here's a PKH of a pub key, which is not just an elliptic curve pub key. It doesn't start with 0, 2. It starts with this guy, and this thing is called an extended pub key. What it means is like this is BIP32 pub key derivation. Check out that BIP to understand what this is. But what it means is like this is not one pub key. This is an infinite number of pub key derived from this extended pub key information. This is called an XPub. That's why it starts with an XPub. And from an XPub, you can derive infinite number of pub keys. So this PKH basically describes all the addresses that are of type P2PKH derived from this XPub. So if previously, like imagine how wallet used to work. It used to work with like storing all the individual addresses, right? Every address is one public key, and if you have to do keychain kind of things, you have to like individually store all the pub keys. But if you can encode that information inside a string like this and have a compiler which kind of compiles this back to all the pub keys that you need to derive, then this whole thing can be represented by this. And then you can play with the internal condition. You can include scripts which are like looks like multisigs, right? You can do more with miniscripts. We'll go about miniscripts, but miniscripts like directly fits into it. Whatever you put inside this bracket could be a valid miniscript, and the miniscript is a high level representation of Bitcoin scripting system. So you can see like we can directly talk about addresses from talking about spending condition. And this is the power of descriptor. And when it goes to taproot, it goes even crazier. For those who knows taproot starts with like there is a taproot node, and then there will be a Merkle tree for each leaves representing one script path of spending. So if there are like multiple possible script paths, then each one of them is like OR of that script. Oh, can you explain taproot? We need to do a whole episode to try to explain taproot, but in essence, this is what taproot is as I described. So if you can follow my cursor, it looks like a Merkle tree. I wish I could draw this thing. Let's try. Uh, uh, yeah. How can I create a new diagram? So a taproot kind of structurally looks like it has something like a key path, and then let's create few more circles. And then let's make some lines. Probably it's gonna take some time, but and then we'll have another line to do this. A taproot conceptually looks like this. So these guys are, say, this is script one. So this is the one of the scripts. So this represents a transaction which is locked by 5 scripts. These 4 leaf nodes and this key node, and this will be script 2, this will be script 3, this will be script 4, and this is called a key path. This is a key path script, and this will be a root, a Merkle root. So a taproot, conceptually, the script structure inside the transaction looks like this. So this represent a transaction that is locked via 5 different scripts. This is the key path spending. This always represent one public key, and these are individual scripts. So this can be a HTLC, this can be a multisig, this can be whatever script you want to write, this can be whatever script you want to write. And the condition of the transaction is satisfied by the transaction is either spendable by the key path, which is one single public key check, just public key signature. That's the key path. Either it can be satisfied by the public key signature thing, or it can be satisfied by any of this one of the script among the 4. If you give the satisfaction for this script, it will satisfy, or if you give the satisfaction of this script, it will satisfy, or this. And how does it work? Like, so all these scripts, imagine these are like Merkle leaves. So just do Merkle tree operation. Has this script, create a root, like concatenate the hash and hash it together, create a root here. Hash this to create a root here. Hash this to create the root here. Whatever the pub key of this root, tweak this pub key with this root integer. By tweaking, I mean elliptic curve multiplication. So the basic operation that you do for private key pub key generation, the same thing. This is an integer, which is a Merkle root of this whole tree. This is a public key. Tweak the public key, multiply by that public key with the root, you will get another public key. That public key goes inside the script pub key of the transaction output. So there will be a transaction output that is represented by this. And this will be called tx out. This is we call it tx out structure, and inside the tx out structure we'll have a value which is like, say, 100 sats, and we'll have a item called script pub key. And the script pub key will be op, if I'm not wrong, this is an op1 and then a public key. And this is how the script pub key will look like. Yes, op1 and public key. Let's put it into quote. Is it even visible? I'm not sure, but yeah, probably. So this is how a taproot output script pub key look like. And this public key is what you get from this public key multiplied by this root. This is like as simple as taproot I can go. Everything else is like there are more details about it, how you do the whole thing. Does that make sense?
Yeah.
Okay, cool. So going back to what we were talking about in descriptors, so now you can map the taproot descriptor. This is the taproot descriptor, how semantically look. This is the first public key that goes over here. This guy, the key path's public key. Then you have the first script. This is the first script. This is saying like anything that can be unlockable by the signature for this public key. So this is talking about script number 1. Then it's comma next script. This is like public key. This means like any signature that satisfies this public key is a satisfaction for the next script. So this descriptor describes a 2 script path and 1 key path taproot spent. And then here's the example where you can go more complex. You can say like, here's a taproot descriptor where this is the key path, but the script path is one single script. Instead of dual script, you just have one script. And this script is a sorted multi. It's a 2 of 2 multi. So that means this transaction is unlockable by either the signature of the first key or the satisfying the multisig that is involved in the script 1.
So I have a question regarding xpub.
Yes.
So I think, like you said, almost infinite number of public keys we can generate from it. So does the wallet like iterate through each of them and check if there's transactions for it, or is there some easy way to do it?
Oh, that's a good question. It's not an easy way to do it. Like that's a very crucial part of wallet engineering. You have to keep track of all the used indexes and all the indexes that you have given out to, and all the possible indexes that you can have transaction in, because you cannot possibly search through an infinite search space, right? So but it's not that tricky. It's easy to do, and you just have to keep looking. This is called a look ahead. So the wallet will scan. So wallet will know, say I have given out, I know that up to index 10 all the transactions are used, like there are existing output using those addresses. Up to index 20 I have given out, and then it will keep an buffer of like 20 plus 10, a 10 buffer window, on top of which it will try check in case if I have an output address in a transaction in that index, I should be able to catch it. And then it will track all the indexes that it has given out. So the number 20 will increase, and then the buffer window on top of 20 will increase. And that's how it will keep on progressing through the index system.
Okay, I got it. That makes sense.
Yeah, that's a good question. So yeah, so that's what a descriptor is. And this is like this whole scheme of descriptor has been used mostly to keep wallet engineering simple and trying to create a common language for wallets to use a certain formatted string in order to create different kinds of things. The reason for doing this in a string way, and why not just like wallet does their script management system like internally, right? Why not just programmatically create structures? Anybody has an idea like why strings like that? Why not like create a library in Rust or C++ somewhere where you say like, hey, This is a descriptor management system, and import your descriptor management system in your software if you want to include it.
I mean, you can share among different wallets, I guess.
Yes. So you can easily copy the descriptor from the wallet and get a string and pass that string around and share it with other people. Not only just other wallet, but when you go into complex Bitcoin scripting, say starting from multisig to any kind of thing like HTLCs or other kind of like inheritance locking or vault locking system, you need to like pass around the data. You need to pass around the data of like what they need to sign for, and this has traditionally been a very challenging problem of trying to do complex scripting policies with Bitcoin. If you have n number of parties involved in a complex policy structure on ownership of a fund, how do you very easily send around data to wallets, that different wallets they need to sign different parts of the transaction at different time? Descriptor make that possible. It makes the descriptions, it makes the description of the tracking mechanism of entire scripting system that your wallet needs to manage exportable. So your friend's wallet just need to manage um, the corresponding part of that descriptor, and then just copy paste it and import it in their wallet. And your wallet, if it has a descriptor compiler, then there is of course like these libraries which are used as descriptor compiler, and then the descriptor compiler will be able to figure out what kind of addresses you are looking for, what kind of address the wallet should be signing. Okay, so that was a long one on descriptor, but yeah, Miniscript is even more involved. So before we move on to Miniscript and stuffs, um, any other questions? In the meantime, I'll try to find out some good tutorials that will be useful for you guys to scour later. So here is a tutorial that uses BDK CLI specifically, and this was basically interestingly written by one of our community members, Sandipan Dey, and he is working in Galloy. He wrote this tutorial last year, and it's a very nice in-depth tutorial of how to operate with descriptors. So what he does is like he shows like how to create multi-signature descriptor and create a BDK CLI wallet. For those who don't know BDK CLI is the only command line wallet out there that it's a command line wallet tool that allows you to copy paste descriptor inside it and do wallet operation like create transaction, sign transaction, get addresses, get balances on those descriptor, and you can swap in descriptor in and out, and it becomes like this descriptor operation framework. So it in the start it goes into how to set up BDK CLI and start off it a bit of description of miniscript and descriptor, and then it goes on creating multi-signature descriptor between two wallets using, so here's it's going on into command line, and it will create multi-signature descriptor into two wallets and sync it with a Bitcoin Core RPC node. And you will see like how in the middle of the tutorial you just have to pass on, copy paste a private part of the descriptor. So one wallet will have a private part of the descriptor and another wallet will have the corresponding private part of the descriptor. And that's quite interesting because that's something you can do with descriptor wallets. Let's take an example of a multisig. For example, here's a sorted multisig, right? Look at the definition. The sorted multisig says like any one of the two keys. So this is an xpub and this is an xpub. If you change this xpub into an xpriv and import into a BDK CLI wallet, the BDK CLI wallet will know how to sign for only this public key in that script pub key, in that multisig script pub key. And then on the second BDK CLI wallet, you will pass on xpriv. So in the first BDK CLI wallet, it will get a descriptor where this guy is xpriv, this guy is xpub, so it only knows how to sign for this. In the second case, it will get this guy is xpub, this guy is xpriv. So the second wallet only knows how to sign for xprivs. So Just by changing the extended public key from public to private version, you automatically give the signing mechanism to the wallet. Now the wallet readily knows how to sign for a particular transaction. So wallet 1 will only sign for the first public key of the transaction. You will create that transaction, you will pass that transaction to the wallet 2 and tell like, hey wallet 2, like the first signature is there, sign for the second signature. The wallet 2 knows the xpriv of the second xpub and it will go ahead and sign the one. Then it will send it back to wallet 1 and the wallet 1 will check all the signatures are valid and it will broadcast. So that's a basic multi-sig inter-party workflow look like. And as you go more complex from there, you can go more complex into many things and you will need all those interactions at every step. So that's where like descriptor becomes very powerful.
So is that where PSBT, I've heard, is
Yes,
that
exactly. That's where also PSBT comes in, because when the first wallet signs and it will create a transaction, it will not create just a transaction, it will create a PSBT. And you can see, think of PSBTs are as wrappers on top of on top of transactions with extra metadata that is required for the counterparties to sign. So PSBTs are always involved in this kind of multi-party protocols.
okay?
Any more question, or else we'll move on? Okay, let's move on to the more juicy part of it, is like, what is a miniscript? So this is a descriptor, output descriptor, output script descriptor. It basically, the name suggests what it is. It's a description of output scripts. That's simple. But what the hell is a miniscript? So miniscript is something that is kind of like a programming language, but it's not a human writable programming language. So if you go through the description of the miniscript, it says miniscript is a language for writing a subset of Bitcoin script in a structured way, enabling analysis, composition, and generic signing and more. So it is a subset of Bitcoin scripts. And Bitcoin, what are Bitcoin scripts? Bitcoin scripts are opcodes and values and operations and all that thing that you do on the validation part of the Bitcoin transaction, right? So you get opcodes from the script pub key, you get opcodes from the witness, you concatenate them together, and you do the Bitcoin script execution, which is like a very old form of computation on a stack-based computation system. It's very hard to write scripting system as well as complex scripting system, especially complex scripting system with Bitcoin. Like the script system is like, it's like writing games with assembly language, and it is possible, but it's not fun. It's not something you want to do, and there are like so many ways it can go wrong unless you are a Bitcoin script wizard or something. That's where Miniscript comes in. Miniscript is like a high level language on top of Bitcoin scripts. You can think of Miniscripts as like the first language probably written on top of the what is the name of the like the lowest one? I forgot. I just used the name recently. Anybody?
So language is script, right? So they call just script.
Yeah, it's just the scripts, yes. And so Miniscript is like the first language or abstraction layer on top of Bitcoin scripts. And what it is like, there is a playground. We'll talk about playground in a bit, but what it is um yeah, these are the Miniscript fragments. These are called Miniscript fragments, and these are one-to-one mapping with a portion of Bitcoin script. So if you are familiar with Bitcoin script, you might identify them. Like this is a op dope, this is a op hash 160, this is an op equal verify. So this is a Bitcoin script template. And this Miniscript fragment directly translate. It's not a compilation, it's one-to-one mapping from this kind of fragments into Bitcoin scripts. And these fragments are designed into such a way that these are composable. You can compose one after another and create a complete Bitcoin script.
Yeah, I'm a non-computer science guy. So what's the difference between it getting compiled into the Bitcoin script and its direct one-to-one translation? Like what's the
A
difference?
compilation, yeah, technically, like the difference would be a compilation requires some kind of processing. Like you are like doing a lot of like routine processing something. I think like somebody from the call can even describe it better than me. I'm also not a computer science guy, so that
I think what you're meaning to say is like assembler. So this works kind of like an assembler.
yeah, this kind of like
Yeah, it
works
just
like
maps from
it's just
the.
like maps from this fragment to this fragment, and then you can compose these fragments together to create a complete script. And in that
Yeah.
way they mean, like I have read many places like where they say like it's not a compiler, like you can also think of it as a compiler. Like there is a thing called Rust miniscript compiler, and if you run a miniscript compiler on top of a miniscript string, it will give you back a Bitcoin script. And it feels like compiling, but what it's doing is like mapping each miniscript fragment to the corresponding Bitcoin script fragment. And this is like the strict definition of this mapping. It doesn't go beyond this. And it goes into, this document goes into a lot of details of like the properties and the guarantees and all the things, all the rationale behind designing it in the way it does. Like we'll not go into the details of Miniscript, there's a lot, but it is gives a lot of interesting properties and guarantees. And we can look this inside the code also. Like inside code, we'll also take a look at code at many places. So here one place where it fits is like inside the code there is source in script.c. In the script module there is a file called miniscript.h which defines the entire miniscript definition. There is another parallel miniscript definition in Rust, which is Rust miniscript, and these are like independently written. The Rust miniscript was probably written first, then the C++ miniscript was written, and this is the C++ miniscript definition, and this is like the fragments, and you can see like each fragments are like referring to certain script script template. So what is the point of doing all of this? The point of doing all of this is now you can write a Bitcoin script that looks like this. And what does it do? It does a lot. It literally does a lot. You can say this script looks like, so you can like readily read if you are familiar with if else clauses. So this is an and of two things, a pub key A and this guy. This guy is a whole script fragment. So this and this has to satisfy together. That's the first path of the script. Then the OR goes more inside. So OR of this, a public key by B. So public key by A means a signature for the public key of A is satisfies this path. Public key of B is the same thing. Signature for public key B satisfies this. Signature for public key C satisfies this. And this clause is saying either public key B or of this whole guy, which is another OR of either public key C or older than 1000. So can you see the nested nature of the script? So this is our overall AND of this guy and this guy. Any of this has to satisfy. So B comes in and signs and saves the day. If B doesn't come, then we fall back to C. C comes in and signs, saves the day. If C doesn't come, we fall back to waiting. After 1000 blocks, it satisfies, then A comes and saves the day.
So this is similar to like Taproot XML which you showed, right?
Yes,
but I guess then
this is exactly similar. This can be one script path inside a Taproot. So in Taproot, script 1 can be this guy, right? And then you can have like more complex stuff. That's like Taproot takes this into insane level. Now you can have each one of this can be a complex miniscript like this.
What does the 9 mean there?
Yeah, so 9 means is like 9 at this syntax means like probability. So this probability comes in the position of stacking system, like the script system. The compiler will go and check like, okay, so signature by public key C is more probable than waiting for older block, and it will construct the Bitcoin script accordingly so that public key C is like easier to reach, and that will reduce the transaction size of the witness. That will reduce the witness size of the transaction. So this is where this 9 at or any kind of probability system comes in. And it matters whether you put the older lock first or the pub key lock first in the actual Bitcoin script, and the witness size will depend on that. So if you have to go by older, the witness size have to go to the maximum that the transaction possibly can have, right? The smallest size is probably this guy or this guy. Witness size is smallest. So here, like, this gives the script writer a way to tell the compiler that I want this lock to go faster, like go first and then this lock, and that allows to reduce the transaction size in the most probable cases. A same kind of thing goes in Taproot also. This key path spending creates the least witness transaction. So the entire Taproot structures or the script policy structures are defined in such a way, at least recommended to define in such a way. Always have your most probable condition, if you can, reduced into one single pub key spend. And most of the cases, by being creative, it is actually possible. So the most probable cases for your organization or your policy structure to spend the transaction will fall onto key path spending, and the script path spending are more complex, and there the witness size will go more higher, and you only want to do that when you need it. So this is where also like this 9 comes in. Does that make sense?
Oh, this is beautiful. Yeah, thanks, Raj, for explaining.
Yeah. And so here, let's take this policy. This website also has a compiler running behind it, which is the C++ compiler in Bitcoin C, like this code base, exactly this code. And if we do compile, this is the miniscript. So this language is also not miniscript. This is the miniscript. And you can identify different kind of miniscript fragment. But these miniscript fragments are hard to write. Like you can see, like there are so many variation of AND. Like there is an AND OR, AND V, AND B, and N. Different kind of miniscript fragments of ANDs. And then there are different kinds of ORs. It's up to the compiler to decide what's the best fragment to use. You just have to specify in the policy code. This is called a policy language, and this is the most high level language of writing Bitcoin script. Recently we have even a higher level language which goes, and we'll talk about this. This is this website min.sc. It goes even like crazy, but this is the most high level we have so far, the policy. And the policy compiles to a miniscript, and the miniscript compiles to the Bitcoin script. This is the Bitcoin script assembly language looks like, right? And imagine writing this up. Imagine writing this whole thing up with all the pub keys, right pub keys at the same time, and like figuring out what's the right structure for this script should be. Instead, it's much easier to find out what the policy should be. Right? So this is where miniscript comes in to allow us to write more complex policy and on Bitcoin scripting system. And why this is important? Because this actually allows Bitcoin to go into the DeFi layer, like decentralized finance or distributed finance that we talk about in the blockchain space, right? Why Bitcoin doesn't have this DeFi system? Because it's very hard to come up with like Bitcoin systems like that. This is like, unlike like blockchain where they have like solidity and like their entire language system like that, because Bitcoin scripts are Turing incomplete, you cannot have like a very easily abstractable language on top of it. The language is very restrictive, inherently Bitcoin scripts. So you need to have certain abstraction which allows you to write complex policies even in the constraint and the boundaries of the script, Bitcoin scripts. And you can have like, now here's why it's analyzable. Like in the first line it says like it's an enabling analysis. Like this is the analysis. You can know what the script size will be. You can know what the input size will be. This is the script pub key size that will go into the output of the transaction output. This is the input that will go into the witness. Delsin has a question. I think that's what they mean by I lost the chat. I think that's what they mean by saying Miniscript is not a compiled language. Yeah, basically, yeah. Because after this is like one-to-one mapping. And then it allows us to create the total weight, and these weights are very useful for calculating things like what should be the fee for the transaction, how should we bump fee for unconfirmed transaction involving complex scripts, and these are like important questions to answer in wallet engineering, right? And then you can see like there are examples of lot of various scripts. For example, this is a single key policy, pk of key 1, right? Single key, one of two key, or pk of key 1, pk of key 2. So or of pk key 1 or of key 2, as simple as that. One of two key, one likely, one unlikely. So same or with the likely unlikely flag, right? A user and a 2FA service need to sign off, but after 90 days, the user alone is enough. That's a cool one. That's how it looks like. And PK user or 99 by PK key service or older by this guy, which is something very similar to that example script that we looked for. And this is how a resulting script structure looks like, right? And this gives us what happens, we analyze. So this is the analyzation of this miniscript. This is the miniscript script fragment, and same thing, script structure, it gives us the size of the bytes in script. And yeah, this is probably the same repeating thing of the script pub key, this 77 weight unit. And if anybody doesn't know what weight unit is, look it up. It's a way of measuring the weight of Bitcoin data. It's a little bit different than bytes. Is almost like number of bytes divided by 4, but not always. And it has a lot of nuances behind it. So that's it. But you can think of like kilograms or grams or milligrams of, it's like weights of Bitcoin data. And this is how transactions are weighted in, this is our fees are calculated in. So we always talk about weight units. So that's how a 2FA service looks like, a 3 of 3 that turns into a 2 of 3 after 90 days. That's a cool one. This is done with a threshold policy. A threshold is a descriptor, top level descriptor, which goes like, it goes beyond multisig. It goes say like any of the three of any of the n of all the possible miniscript fragments have to satisfy. So this is a list of 3 miniscript fragment, 1 fragment, 2 fragment, 3 fragment, 4 fragment, sorry, miniscript of 4 fragments. Any 3 of them has to satisfy in order to unlock. So that's a threshold. And we could do threshold previously, but writing thresholds are very tough. And so this is like what the final script sig look like. It has a swap going on, then add and swap and op if and else, then not equal, and then finally an op equal. It's very to reason. Even if you look at this, it's very hard to reason what this script is talking about. But if you look at this is like readily readable. Okay, that's a policy that I can understand, right? So it also kind of makes so Andrew Chow had a nice comment on descriptors and miniscript itself. Is like descriptors and miniscripts are not like publicly readable, but it kind of like engineer readable. Like if you are an engineer and if you know the basic definition of this guy, it's very much readable. But if you go to a normie and say like, hey, they can't even read address, like even developers can't read address, but even if you tell people to read this, they might go a little bit trembling about it. But if you explain them what this is like very readily readable. While as like this is even not developer, engineer readable, right? So this is some Bitcoin script magic going on inside. And now we have yeah.
So does it ever happen that Miniscript sort of compiles the Miniscript gets converted into multiple Bitcoin scripts, and then it's checked as to which of these scripts has lower cost, like lower weight units, and then that script is the one that it displays.
I
Or it
think internally it does something like
does
that.
something like that, right?
Yeah, it does something like that because internally a miniscript can be represented via multiple different Bitcoin scripts, and then the compiler checks for minimizing the weight and select the most optimum one.
Yeah.
Yeah.
It's very difficult to get from Bitcoin script directly. It's very
Yeah,
difficult to
it's
jump
very
directly to Bitcoin.
difficult to go the other way around. Like if you have a Bitcoin script, there is a way, like inside the Bitcoin script system, in the miniscript descriptor, I remember checking it somewhere. If let me see if I can find it. Descriptor.h infer descriptor. This function is like the top level function that basically here the documentation defines what it says, and exactly what you mentioned, like it also mentions over here, is like this function takes in a script, takes in some signing provider, and if the signing provider has enough data inside it, then it can find back the exact descriptor that describes, including the miniscript inside it, that describes this script. So there is a way, but it will not give like as deterministically as going as the other way around, right? If you write this, the whole compilation logic will give you one single script, one single script with signature. And but if you get only the script, then you might not get back this thing, you might get something else.
Got it.
And then it goes into a more complex script system. So this is an HTLC lightning. Now we are talking about bolt 3 lightning things and HTLC policy. This is a fairly complex, even engineer readable policy, but at least you can like sit yourself for 5 minutes and figure out what this policy looks like. And this is the giant script. Almost something goes inside the lightning network. The lightning network is built out of a script that looks like this. And there are many like layer 2 protocol like side chains and swapping protocol that uses script that has structures which is similar to this. And so that allows you to describe all the complex scripting systems. And then it's up to you to imagine how to create this. Even this is not friendly enough to play with stuffs. We'll go with the next thing, the next higher abstraction that we have on top of this script compiler, that can be used to create actual, like, then we actually feel like talking about writing smart contract code. It looks like code. And you can do coding logics and if else and loops like and functions and things like this. Not loops but functions. So any questions on Miniscript before we move on to something else? I know this has been a lot for anybody who is looking at Miniscripts and stuffs. Going through this tutorial helps a lot. If you want to go deeper into Miniscripts and like really gets your hands dirty, then I would recommend this repo. This is the only tools out there in Rust. This is a small command line tool written in Rust, and this has some examples. And so here, this is how you create an wallet with a particular descriptor. Create the descriptor string, get the descriptor string from wherever you can, handmade it, write it, use other functions and libraries to create it, and just run wallet with this descriptor and sync if this descriptor and all the derived addresses with this that describes by this descriptor has balance in it. After syncing, you can call like same command descriptor sync. Do you have a get balance? You will see balance coming out. And this is a tool that is very fun to play with. I have been working for past 2 years on this tool, and this is something that I use often on trying out different miniscripts. And this tutorial is that describes like how to use this tool to do something cool, like very basic but cool. At the same time, at the very last, it goes into some goodies where it Yeah, smart contract with Bitcoin. It actually creates a miniscript that goes like this. It goes beyond multisig. It's an OR of public key E or older or public key C. So this is like an employee-employer contract. And this contract describes a relationship between an employee-employer where an employee gets a fund if the employer signs in, or else it gets the fund after 90 days. And after certain days, yeah. And this is one fun thing to try out. And so this is the last thing. We have last 10 minutes. This is the last thing we wanted to talk about in this session. This is the main. See, this is so cool. So this is a Miniscript based scripting language for Bitcoin contract. This is a web app. This guy works on top of Rust Bitcoin. And just to quickly show on what Rust Miniscript is. So Rust Miniscript is the Rust version of the Miniscript compiler. It compiles both descriptor and miniscript. So it basically works on descriptors that we saw in the Bitcoin CLI information. And this is a library that you can use in your wallet product to create this library. BDK builds on top of this library. And so this guy is a language built on top of that library. And this is how it looks like. This is a liquid like federation. This is a liquid network. And liquid like federation work is this. A federation is defined by 4 of 5 pub keys. Pub key A, pub key B, pub key C, pub key D, pub key E. This is a federation that is a definition of 4 of 5 pub key. A recovery is an emergency path that is a definition of 2 of 3 pub keys. And then timeout is a timeout that defines after timeout this thing satisfies. And the whole final script looks like this, likely via federation or via timeout and recovery, right? So most of the cases, block production in liquid will follow likely via federation. Federation members, 4 out of 5 guys signs in. If something goes wrong after this period, emergency guys can drop in and recover the funds. This is how the policy of this whole thing looks like. So this is the policy definition, which looks very similar to the Miniscript definition also. This is the Miniscript descriptor. So you can basically copy this string, go to BDK CLI. There's easier way from my GitHub to go to BDK CLI. Go to BDK CLI. Here in this instruction, here you have the WPKH descriptor, but just paste that descriptor, paste that string, and you have a liquid federation running in your rectest node. How cool is that? Right? So this like literally takes it to its level, and this is the final Bitcoin script, like the Bitcoin assembly language script looks like. It's impossible for you to write it, even to parse it. There's a lot of things going on with stacks and formal stacks and a lot of push bytes and operation, but at least you can read the descriptor and the miniscript and can trace like, okay, this is actually like satisfying this this policy, right? And then this website goes into next level and defines the language basics. So this is how you can write a logical operator or things. This is like traditional pre-image based HTLC. So public key or hash, this public key of A or hash that satisfies like the pre-image hash, like if you know the secret that hashes to this H, or public key of B via a timeout. So this is the traditional HTLC lightning, right? And this is this guy, and this guy. This is like a traditional threshold. This is how you can write 2 of 3, 2 of this list, right? And then you can do execution probabilities. You can say likely instead of putting numbers. You can say likely A or via B. You can even say likely via branches, likely A or via this thing. This thing is this guy or this guy or this guy. So just like how you do like logical operations in programming, you can like combine and match together different spending policies and create your smart contract system, right? And then you can do time and duration. You can give like direct date, like after this date this is unlocked. You can give like relative time locks, like after 90 days it will unlock. You can this language, this website also knows how to parse like 1 month 2 weeks kind of things, also knows how to do hour kind of things. You can do block kind of things also, right? And then you can define variables, like this is a redeem path, and this is a refund path, likely via redeem path or via a refund path. So, and then you can like construct complex structures out of this. This is the same liquid federation we talked about. We can do arrays, like this is keys, or these are keys, so key either keys dot zero or via keys dot one. You can say certain like CEOs or directors. So directors are list of keys, so you can say either by CEOs or by any of the director. Any means one of three multisig for this thing. So any of the director can sign or the CEO can sign. You can say either the CEO can sign or all of the directors has to sign, right? Then you can do public keys. You can put public keys in a variable, write contract like a public key. You can do like the xpub variations. You can put different xpub indices, like saying xpub but various index number going into different policy paths, different paths of scripting conditions. So this path spends by alice/0, this path spends by alice xpub, this is an xpub via one, and these are like entirely different keychains. These like all the keychains from here will not match with each other, and you can like construct a policy that handles like one xpub, but it xpub has multiple branches, each branch going into different policies. So this basically gives the whole, you can do functions and stuff like that. They went really insane and created everything that they could create out of this. You can write functions, and then your basically policy becomes the function, and here you are basically like, this looks like solidity now. This starts looking like solidity, where you are defining your contract function and then just playing the contract function. What is the contract function? A contract function will eventually give you a Bitcoin script, which is basically an address. Same thing that happens in Ethereum. You write a solidity code that is compiled back into an Ethereum address. This is where we get to that level where we are finally capable of writing it. So yeah, now I want to take a break of like rambling about miniscripts and stuffs and how good they are, and take some questions or any general comments and discussions if you guys want to.
Are people using mini-sc, like min.sc, or they're mostly using Miniscript itself?
People generally, while building wallet, you don't want to use min.sc. Min.sc is for wallet developers to generate their miniscript string. After generating your miniscript string, you want to use something like BDK, like not Bitcoin BDK CLI, but a library like BDK, which gives you an wallet framework, which basically works on miniscript descriptors. So this is what they want to use. MinC is mostly as a playground. It's not a wallet developer tool. It's mostly for playground. It's for imagination, for as a script policy maker. What should your miniscript look like? For example, suppose you are a developer in Liana wallet and you are interested in creating vault-like system. You can conceptually describe your vault, get the miniscript, and create the miniscript wallet using that BDK wallet. And if your user base is like they will only use that vault, no other complex random miniscript, then you can like you have a wallet software that is running using BDK with your vault arrangement. So that's what mostly is used for. I don't know anybody who has used min.sc as in their development exercise or stuffs like that, but I can imagine like anybody who is thinking along that line. At the same time, there are not enough many people in the world who are thinking in this line. Like it's very recently that people started talking about miniscripts and stuffs, when because doing miniscript is not only just about having a software or language or library. You kind of have to have a ecosystem wide support. Like a lot of wallet needs to know how to interact with it, lot of backup system needs to know how to interact with it. One of the major engineering challenge that comes up in miniscript based wallet, which are not there in regular Bitcoin wallet, is like, how do you back up a miniscript? It's not about just a seed only. A seed is not enough, seed words are not enough to back up this whole thing. So you need the whole information encoded in this thing. So how do you back up that thing? How do you easily store it? These are like open questions. Hardware wallets wasn't using miniscript. So just if you have a miniscript wallet doesn't mean you can like sign stubs with your hardware wallet using it, because your hardware wallet doesn't know how to sign with miniscript. So hardware wallet needs to get support. So, but recently there has been a lot of people who gain traction on miniscripts because it is so usable and it um, allows flexibility. Right now, if you have been following the market noise or like the trend that is going on in miniscript, is like mostly for vaulting and multi-sig wallets. These are the major applications that are using miniscripts out there, and the hardware wallets are now have a reason to support miniscripts in their hardware, because they want to provide service for multi-sig guys and vaulting guys. And as more and more, it's up to like how many application you can come up with this thing. Just because we have this cool way of doing thing, and even like this is where taproot kind of structures, this kind of structure fits in perfectly. Like with taproot, now in taproot you can imagine like this main.sc doesn't support taproot yet, but if it would, it will give it a very simple taproot descriptor at the end, which multiple paths, these ors will be each of the paths, and you can have multiple ors, and then each ors will be like one script path of the taproot, and then you can have like as many or paths as possible. Previously what was the problem was like you have to have the whole script. If your script is very large, you have to have the whole script inside your spending transaction. But with Taproot, why we want Merkle root? Because we don't want to get the whole script inside the spending transaction. We might want to solve via only script 1. Taproot allows us to only put script 1 in the spending transaction and not put script 2, script 3, script 4. That's where the real efficiency of Taproot comes in. Taproot is not much efficient for regular transaction. If you have a one-of-one public key, just public key and signed by the public key, that's as simple as key path span. But when you have like, say if you have like a structure that is like 10-15 leaves, if you try to condense it down in a normal transaction, that will create a spending transaction that will be easily over 1 kilobyte in pre-taproot world. With taproot you can condense that thing down in probably the size of one single spending path, and one single spending path can easily be like 200-250 kb, right? And that also provide like privacy. Like you just like anybody watching at the blockchain will only know like, okay, script 1 is one of the spending condition of that taproot, that they don't know about script 2, script 3, script 4. So these are still hidden. So that also allows privacy, that also reduces footprint in the blockchain for complex scripts. But now the question is, can the market come up with like use cases for complex scripts? So far we only got vaults and multisigs, but yeah, the possibilities are kind of endless when you start thinking about programming in this kind of form and language.
So what is that address? I thought it was a pay to taproot address in
This guy,
min.sc.
this guy.
Yes, yeah.
Oh, no, this is a normal. So the address type is WSH. You can see it in the miniscript. This is a witness script hash. And
Oh,
this
okay,
is a
okay,
P2WSH address.
okay,
And the
okay.
TB1 basically it needs for, this is for testnet. This show like, yeah, you should not spend fun to this guy.
Okay, fine. It's just a sample address.
Getting Bitcoin in is easy. That's a fun one. Getting them out is not for testnet use only, right? Yeah, like you might not be able to satisfy this guy if you don't have like private keys for all the
Right,
public
right.
keys you have provided. So,
And you won't have, yes.
but you can spend to this, right? You can spend to this. You can like
Yes,
send
yes.
fun to this guy, right?
Yep.
So,
Okay, okay. So yeah, I think that would be something which we can add on to making the taproot version of this.
yeah,
Right.
yeah. So in
Interesting.
Taproot, you will also have a Taproot address, which will
Right.
be same. It will look like TB1. Instead, in the miniscript, instead of WSH, you will see TR.
Right. Right. Okay. And is it a new opcode in taproot?
No, there is no new opcode. There are few opcodes that are extra defined in the Taproot scripting system. Taproot kind of redefines a scripting system called TapScript, and they define two extra check multisig variation. But that's the only variation. All other opcodes remain same.
Okay.
Raj, so we will have another peer review on Miniscript, is it?
Yes, we'll have another peer review on Miniscript where we will go from with like selected questions from this one and the next one. Not all the questions, because many questions are internal and implementation dependent question. But we will select general questions for first part and second part, and we'll go through it. And I'll try to come up with a list of questions. But in any case, like for the next one, we will look into a bit of code. We also have like a bit of code part to look at, and there are some interesting discussion there. We'll more go through the questions and the code in the next one.
Okay, so for example, for this one, I didn't brush Taproot or output descriptor, so I should have done that before jumping on this call.
But that's okay. Like that's the point of this call was to get the ground ready for all of us for the next one. Because yeah, so
is there any study material or is there any link that you would suggest? I mean, there's a week.
I would just suggest like go through this thing. Go through just these two docs, these two peer review club, and the first part is we have in the link here in our issue, and the second part link is in the first part itself. Just go through the doc. Whatever you understand, that's okay. Whatever you don't understand, that's also okay. But we'll keep our discussion around these guys.
Perfect.
So, okay, so we'll end with today's discussion. This was a really nice and productive one. I actually like didn't had a lot of planning, like how it will go, and kind of like wanted to let the discussion flow around where it goes, but wanted to cover the basic ideas of Miniscript and all the things that somebody interested in Miniscript needed to know. And on the next one, we will dive a bit deeper. And thanks for joining in, everybody. We'll see you guys on another review club 2 weeks later.